Hi everyone, welcome back to the Technion's ECE Deep Learning course. I'm Tal, and in this video we're going to see a new type of data, sequences, which include sentences, stock, videos, and more. We are going to focus our discussion on natural language processing, NLP, because we want to understand how we convert words or strings to numbers that can be fed into a neural network. From that point onwards, the process is similar for other data, such as stocks, that already arrive in numbers form. The main question we are going to ask today is how we deal with temporal data, where we have temporal dependencies between points. So let's begin. Okay. So far we have dealt with tabular data and images in the previous tutorial, but what about text or other type of sequences? Sequence modeling is the field of modeling sequences, so for example, text sentences, videos, stocks, trajectories in reinforcement learning, autonomous driving, and more. For example, another example is weather forecasting, which is also very popular. Now, unlike our previous assumption that the data we have is IID, this is not usually the case in sequences, right? Because if you randomly change the word in a sentence, it would be very hard to understand its meaning. So if we have the sentence, where is the dog? And we scramble the word, so is the where dog? That makes no sense at all. And of course, if you want to model or perform some task on this sentence, you need to consider the order of the sequence. Okay, now, also, these are words, they are not numbers, and we can't actually feed these directly to a neural network, so we need some pre-processing to do before we can actually use it. Okay, now our focus is going to be on NLP and natural language processing, but once we are done converting the strings to numbers, everything is the same for other sequences that already arrive in numbers form. Okay, so let's talk about something very popular today, which is language models. And the idea is that we have a sentence, so we are going to treat or denote the words as x0 to xn, where xn is the last word in the sentence. And we want to model some probability over this sentence. Now, the most popular method is to factorize this distribution using the basic probability principles and sometimes also the Markovian assumption. So we can factorize this probability here by taking a look at the probability of the first word and then condition on the previous word. We can model the entire series. Now you can see that the dependency here is only on the last step. So this is a Markovian assumption where we only depend on the previous time step and not the entire history. Now, this is usually not the case when we work with sentences because, for example, what time is it? So it refers to time, and time is not the previous. It does not come before it. Okay, so the Markovian assumption is not the best approach, and this is why we want our models to consider or to look at the entire past in some way or form. So. Neural language models. So how do we do this? How do we implement this in the era of deep learning? So there are classical ways to build language models, but the focus of this course is deep learning. So we will leave the classical approaches to the various NLP courses. If you're interested, go ahead. It's good. So the first question we ask is how do we convert strings, which are usually come in characters or words, to numbers that can be fed into a neural network? So this conversion is typically termed embeddings. So we want to create word embeddings or part word embeddings or character embeddings. Basically, we input text into a neural network and the neural network will map all this context onto a vector. So this vector is usually represent the next word or the next, what we are going to call token. And we are going to end up with a big embedding matrix, which is actually a dictionary which maps from an index to vectors. And I'll show you an example of this in a minute. The word embeddings contains a vector for every possible word or part words or character that the model can output. Now we already have this implemented in PyTorch, so don't worry, it's nn.embedding, and you need to give it the number of words in your dictionary. This is the number of embeddings and the size of the vector which you want to represent your tokens with. So don't worry, we'll see it in a minute. And at this point, it's good to mention that we already have pre-trained models, very large pre-trained models. So, for example, one of the early models were BERT or Word2Vec, and they have already been trained on some objective to create word embeddings. So basically, when you have text data, you can just download these models and input your word or part words into this model and get a vector representation, which is already float numbers, which you can already use in neural networks. Okay, so what is this word embedding? So it's essentially a vocabulary, right? So we have words. So we get a bunch of, so our data is text, and we get a button, so we can calculate a histogram or something like that, and just count the number of occurrences of each word, and then build a vocabulary based on frequency of words. So, for example, in our case, man, woman, boy, girl, prince, princess, queen, king, monarch. And so we are going to have 9 words in our vocabulary, and we can represent each one by its index, or by converting into a one-hot vector. And early models actually use this one-hot representation, but this is not practical when you have 50,000 words. So you will have a vector of size 50,000, and they are very sparse because we only have one at the correct index. So this is not scalable. So the idea is to create something else. So what we're going to call embedding. So basically we will have an index, then we'll convert it to one-hot vector, and this is the index of a big matrix that actually has the embedding, the vector embedding. So in this case, the dimension is 5. Okay. So in our case, index 2, that means we are going to, so we start from 0, right? 0, 1, 2. So if you take this one-hot vector, this is essentially this cell, right? So this is the embedding. Now, how do we calculate these numbers? How these numbers are calculated? So basically, they are usually learned, right? So this is actually a weight matrix. So this is why we are going to use it as a neural network layer, right? So this layer NN.embedding, this is what it essentially does. It is just initializing a big weight matrix, where its size is the embedding dimension you want. So in this case, 5. And of course, we need the number of words in your vocabulary. So this can grow very large, so from 1,000 to million and billions. Okay. And the process, you can see it here. So basically, we get a sentence, and we take each word and find its index in our vocabulary, and then we convert this vocabulary to this token into embedding. Okay, and then we end up with just a sequence of vectors, and this is what we are going to use in our models. Okay, now, okay, so we now know how to convert words to tokens, to embeddings, but how do we process these embeddings? So how do we learn something from them? So the first neural language models were actually based on convolution, or one-dimensional convolution. We talked about convolution in the previous tutorial. So basically, we will have a 1D convolution. That means we are taking a window, in this case, window of size 3. So basically, we look each time at 3 words, right? So it's very simple. Just like we did with pixels, we now do with words, right? So we have a sliding window of size 3 in this case. So the kernel size is 3. And basically, we do the same. However, this fixed length history means that it can only condition on bounding context. So basically, we only look at the 3 past words. So it's not very. It's of course it's better than the Markovian assumption, but it's not the greatest idea when we want to understand deeper contexts, right? But the upside of these models is that they are very fast. Okay, because convolution is quite fast, especially if it's implemented on the GPU. Okay, so this is one of the earliest neural language models, and this is still, so 1D convolution is still used today, but the most advanced applications are using other type of networks, which is the topic of this tutorial and the next one. Okay. So first, let's understand what kind of tasks we can do we can achieve using sequences. Okay, so we categorize them to several categories. So the first one is, so we're talking about type of tasks. So the first one is one-to-one. So from a fixed size input to a fixed size output. So for example, image classification. So we have a sequence of size 1, right? So basically we have an image and we get a label, and this is one-to-one. So this is what you've done so far in the course in all our examples. And now let's talk about the more interesting stuff. So the first one is one-to-many. Right, we have a sequence output and a single input. So for example, the task of image captioning. So basically we input our model with an image, and the output is a sequence of words describing the image. Okay. Another type is many-to-one. So it's the inverse. So we have an input sequence and just an output, just a single output. So so an example for this is sentence classification or sentiment analysis. This is what we're going to do in this tutorial. So for example, we input a long review of a movie, for example, so it's a sequence, and the output is a label that says whether this review is positive or negative. So this is what we're also going to implement in this tutorial and the next one. So quite a popular task. Now the other two, the two that are left, are both many-to-many. So we have sequence input and sequence output, but one is synchronous and the other one is asynchronous. So let's give an example. So let's start with the asynchronous. So sequence input and sequence output, but we don't have one-to-one correlation between the input and output sequence. So for example, machine translation, when you want to translate between two languages, so you have an input sequence and output sequence, but they are not necessarily correlated, because the number of words in one language is not necessarily to the same number of words in a sentence in the second language, right? So this is why it's asynchronous. The other type is synchronous. So basically we have a label, or we have a target for each input sequence, for each input in the sequence. So for example, video classification, where we wish to label each frame. Okay, so we have a label for each frame. So this is the many-to-many, where it's synchronous. Okay, cool. So we covered the type of tasks that we can achieve with, or we can perform with sequences. And let's get to the main part of this tutorial, and it's how we pre-process the text. So how do we actually process words and convert them to tokens and then to embeddings. And then we'll talk about how we can actually process them with a neural network and achieve or complete the task of sentence classification, or what we're going to call sentiment analysis. Okay, so as I've mentioned before, in the classical NLP, they sometimes used one-hot vectors, so this can grow very large and not scalable, of course. So we are going to do this with embeddings. The general steps are loaded text. So basically you have a big text file in your memory, and now you want to convert it to a dataset. So the first step is tokenization. Basically, you are going to split the strings into tokens. Now, a token can be a word. It can be a part of a word. So for example, the ending and the suffix ing, right? And also it can be characters. So it's up to you what level you want to use. So what we usually do now is part of word. So basically, you can see that the tokenizers just look at part of words, so ing and all of the other suffixes are tokens themselves, and we also have all the other verbs and adjectives and things like that. The next step is, after you decided what level you want to reduce the tokens, is building a vocabulary. So basically you want to build this big table that maps between index and a token. Okay. Now, after we've done this, we are going to convert them to numbers, and this is usually done with an embedding layer. So basically we are going to initialize some parameters, and they are going to be learned, right, using backpropagation, depending on the task you want to achieve. So for sentiment analysis, our embeddings will be updated from the cross entropy loss. Okay. what we're going to do now is practically we're going to load the IMDb dataset, so IMDb the movie sites, right? And it contains movie reviews which are labeled as positive and negative. And in NLP it's called sentiment analysis. Okay, we are going to take a bunch of sentences which are reviews, input them to a neural network, and get the classification if this review is positive or negative. Now we're going to work with torchtext, the sub-library for PyTorch that handles text data. And if you want, so we already have some data sets that we can directly download from PyTorch. But if you want to work with your own dataset or your own text file, so there are links here how to do this. It's not that complicated. Okay, so if you have a text file and you want to convert it to a dataset, it's pretty simple using the torchtext custom dataset. Okay. So in addition to our part of words, we also have spatial tokens that are important, especially in language modeling. They are not that important for what we're going to do in this tutorial for sentiment analysis, but they are important for language modeling. And these tokens, they are signals or signs that are used for to indicate to the neural network where a sentence starts, where a sentence ends, and whether there are words that are not from the vocabulary. So these tokens are SOS or BOS, so start of a sentence or beginning of a sentence, right? So this is a start token. And this token also is going to be mapped to a vector, and this is going to be learned, okay? And usually these tokens these spatial tokens are the first indices in the vocabulary, okay? We will see this in a moment. The next token, which is important, is padding. So this is the most popular token because this is used to pad sentences that are shorter than the longest sentence in the batch. So remember, in deep learning, we are working in batches, and sentences, or in general sequences, can be of different length, right? So here is an example. And what we need to do is we need to pad the sentences that are shorter than the longest sentence in the batch, okay? So we need a token for that as well. So this token will indicate to the neural network that from this part in the sequence until the end, it's just garbage. Nothing here is important. It's just a padding, okay? Another token is the end of sentence. So we need to indicate to the network when the sentence ends, okay? It's important for the neural network to understand the structure of the sentence. So it needs to understand, for example, that the last when you use question mark, for example, then after that there is nothing. Okay, so this is why it's required, but it's usually required for language models. Okay. Another token is unknown, UNK. So basically it marks unknown words. So if the model thinks that no word in the vocabulary is good as the next word, or you decided to leave some words out, like first names that start with capital letters, then they will be replaced with UNK token. And basically this gives the network an ability to say something like, I don't know, what's next. Okay. So here is this figure here depicts what's going on. So for example, we have batches, and in each batch there are 4 samples. So they're basically 4 sequences in each batch, right? And we also need to pad them. Okay, so usually there are smart ways to pad. So basically you collect samples to form a batch that are of similar sizes. So that means that you need to work less to pad, but it's not that important usually, and you just pad to the size of the length of the maximum sequence in the batch. Okay, so we will load the IMDb dataset. So you can see that the structure is very similar to what we did with the image dataset. Nothing here is special, right? The next thing we are going to do is we're going to take a look at this dataset. And what we're going to do is see how many samples we have. So we have 25,000 samples for training, okay? And we can also see the labels that we have. So we have 2 labels, 1 and 2. So 1 is going to be the negative and 2 is going to be the positive. And we are going to convert them to 0 and 1 just for the sake of simplicity, and for just like we did in other classification tasks, okay? And you can see here how we work with this dataset. It's very similar to what we are familiar with the datasets for images and tabular data and things like that. Okay, So let's take a look at an example from this data. So we can just print some sample. So we print here the sample, and you can see that the label is 1, so 1 is negative. And there are a bunch of text, this text describes the review for a movie, and I'm not going to read it all, but you can see that the final sentence in the sequence is, but really this film doesn't have much of a plot. So typically this is a bad review, like a negative review, and not surprising, this is the labeled 1, so 1 is negative, right? So we have a bunch of text and we need to tokenize. So there are different tokenizers which you can use, and we're going to use basic English tokenizer, and usually this tokenizer is also works on part words, okay? But you can see there are several types of tokenizer you can use. You can take a look at the documentation and see what works for you, but we will work with the basic English one, and of course for other languages you'll need to use a different tokenizer. Okay. So the tokenizer, it takes a word, right, and it transforms it to an index. Okay, so we'll be after we are done tokenizing, we are going to build the vocabulary. So let's see how we do this. So first of all, we define the maximum size of the vocabulary. So we are going to have maximum 55,000 tokens in the vocabulary. So your text data can have more tokens than that, but they are going to be discarded and replaced with U and K when we meet them. Okay. Okay. So there's a simple approach to build a vocabulary from your text. So you call this function from torchtext, right? So build vocab from iterator. So you take tokens, right, and you give it the spatial tokens you want to add, so UNK and padding, and you tell it the maximum vocabulary size. Now it's going to count the number of occurrences, so the frequency. It's going to do a histogram of words, and it's going to take the top 55,000 most occurring words. Okay, so anything that occurs and out of this list is going to be replaced with UNK. So let's see an example. So we build a vocabulary for IMDb, and what you can do now is you can convert the sentence "here is an example" to tokens, right? So in this case, these are the tokens. These are the indexes, the indices, right? So the index for the word here is 132. Okay. Now we can also do the opposite, right? So we can take these numbers and convert them to words. So basically you can see that 0 is UNK, 1 is ped, so this is not surprising. 1 is usually the index for the padding token. 57 is good, and 95 is how. Okay. Nice. And we are also going to convert the labels to just 0 and 1. Okay, so 0 is going to be negative and 1 is going to be positive. The reason, it's not that important, but the reason we do this is for simplicity. We are going to use binary cross entropy, so this works better with 0 and 1, and we can also use the sigmoid function. Cool. So very simple. Okay, we have all these functioners that help us convert a bunch of text to indices or tokens, right? And we'll see later in the next tutorial how we use the NN.embedding layer. So basically this layer accepts these numbers, and it just gives you the vector that corresponds to this index. Okay. Now, in this tutorial, we're going to do sentiment analysis. So it's basically just a classification task. We're going to use the binary cross entropy or cross entropy for multi-labels. But in general, when you want to train language models, then the output is not a class, the output is a word, or a sequence of words, right? So many-to-many or one-to-many or these type of tasks. And you need some way to evaluate your sentence, your output sentence, whether this sentence is good or not. There are two ways to do this. So Perplexity is the most general one. We are not going to delve into it, but if you're interested, basically we're measuring the probability of a sentence. And the second one is specifically for machine translation. It's called the BLEU score. And the BLEU score also gives you, it's also an evaluation metric specifically for translation, where the output is also a sequence, but in a different language. Okay, so if you're working with language models, so get familiar with these metrics, but for this tutorial, we're going to do classification. So just the regular metrics, accuracy, precision, recall, all these fun stuff we are already familiar with. Okay, cool. So now what we're going to do is we're going to understand how we process these kind of sequences. So what kind of neural networks we can use in order to form tasks from these sequences, right? So we're going to talk about a class or a family of models that are called recurrent neural networks. Sometimes it's called feedback neural networks, but RNNs is the usual term. They are quite popular. They are still popular these days, even though we have attention and transformers. Then they are still being used, and there are also recent advances that actually bringing them back to the spotlight. So we'll discuss this towards the end of the tutorial, but let's get familiar with RNNs and what are they and how we can use them. Okay, so the idea of recurrent neural networks is using recurrence. Okay, so basically we're going to do some recursive process or a loop, an iterative loop, right? So we are going to save the output of a particular layer and feed it back to the input in order to predict the output of the layer. So we're going to do some several iterations depending on the sequence size, and this is why it's also called feedback neural network, because we feed it back. Okay, so we feed back the output to the same network, to the same layer, to the same network. Now, every time step we maintain some step which received from the previous time step. This is going to be called a hidden state, okay? And this is going to represent what we have seen so far. So basically, we are going to have some memory or some representation of the past inputs, okay? So the idea is that we are not going to be limited by a window size, right? So like we had for the 1D CNNs. Because we are actually representing the entire past as a vector, so we can have some disagreement if this vector is enough to represent a past or a sequence of 100 or 1,000 tokens. Okay, but essentially we have some representation for the entire past. Now we are going to take this representation of the entire past and our current input in the current time step, and using both of them, we are going to decide on the consecutive output. Right? We repeat this process as many times as we need. So the way we are going to understand this is we're going to work with computational graphs, but since we are using the same weights, the same network, what we're going to do is we're going to unroll this graph, so unrolling the graph over time. So basically, the weights are the same, but but the inputs are different at each time. So let's take a look at how this unrolling is happening. So X is our input, right? We're going to have some weight matrices A, B, and C, and they are going to determine our output as follows. So first of all, we need to initialize the hidden state. So the hidden state is usually initialized with zeros or some random numbers that can be a constant or learned, but we need to initialize it. We are going to take our input, multiply it by B, and taking our previous hidden state, multiplied by C to create the hidden output. The hidden representation, and then we also create the output and using A and creating the input to our next step. We are using H. So this is how it's happening, right? So at the second time step, we're going to use our current input and age from the previous output. Okay. And then we are going to create the new age, which is created using both X and the previous output, right? And together these create the new output using the A matrix, and the age is moving on to the next step. So let's formalize this with actual weights, and also see how we can do the backpropagation on this unrolled graph. Okay, now one thing to remember here is that the weights are shared over time. These are the same weights. The same weights are multiplied by the different inputs. Okay, so we have weight sharing over time. Okay, so also called temporal weight sharing. So let's talk about RNN and formalize them officially. And then we are going to analyze and see what the problems that we have, what are the problems that we have with RNNs. So the first thing we do is we create the new hidden state HT. Now you can see that the HT is created as follows. It's a function, so in this case hyperbolic tangent, tan age, and it's a function of the current input, right, and the previous hidden state. So remember that for step 0 we just initialize h0 with something, okay, and ht is then activated with hyperbolic tangent, and the reason we use hyperbolic tangent is for numerical stability. So recall that tan age outputs bounded values between -1 and 1, and since we are going to do this over a lot of time steps, then sometimes we have something called vanishing gradients or exploding gradients in the other case, and we want numerical stability, and hyperbolic tangent help us with it. And this is one of the only applications where we actually use tan age inside of a network as an activation inside of the network, and not only on the output, not only on the final output of the network. So no ReLU or anything, just bounded outputs. And you can see here in animation how it happens. So we have xt, we have ht minus 1. They are both multiplied by their respective weights, which are shared over time. So WH, WIH, and of course the biases. Then we activate them with tangents with tan age, and then we just output ht as the output, which is going to be used for the next time step. Now, if you ask yourself what is the final output, then it's in the case of RNN is just HT. Okay, so where you want to classify or do something else, then you use HT. Okay. Now we're going to analyze this much deeper in a second. I'll just tell you that you can use RNN in PyTorch in its vanilla form, but people don't do this today because there are several disadvantages, as I'll show you in a bit. And the reason why I'm trying to do this is for research purposes. Basically, RNN is an idea, okay? So it's an idea of using feedback, right? And you can actually inherit from this class and implement your new RNN. And you can think of several ways where you can do several things that you can do with it. We will see two types of RNNs. So we will see LSTMs and GRUs, but there are other ways to implement an RNN, and basically you can use this idea. But in its vanilla form, people don't use it today. So what are the disadvantages of RNNs and why people are not using this today? So think about like document reading, for example. So what you do when you are using an RNN, then you are actually compressing the entire path into a fixed size vector at each time step. So the fixed size vector is HT, and it's usually something like 128, 256, 512, these kind of sizes. So you are actually compressing the entire path into a single vector, which is sort of a bottleneck, right? You can think of, is this size enough for documents of this size and things like that. Okay. Now, when you do this for a lot of time steps, then we actually usually see something called gradients vanishing. So gradients tend to vanish, and we have ways to solve it, and I'll talk about them in a bit. But it's still a problem. Okay, so long context are pretty hard for RNNs to model. And in its vanilla form, it's not possible to parallelize over time steps. So in each iteration, so for example, for word number 10, we need to wait for the previous 9 words to be processed, right? So the training can be slow because we need to wait for the previous output, okay? Now, how do we actually train these kind of networks? So we are going to introduce a realization of the backpropagation algorithm. It's going to be called backpropagation through time, BPTT, okay? And it's relatively straightforward to implement this. It's just regular backpropagation, but on the unrolled graph. So we are going to draw this graph, but we're going to unroll it over time. And basically the weights are going to be the same. So each weight is going to get gradients from different time steps, okay? So this is a specific application of propagation in RNNs, and actually in practice we unroll the computational graph and we obtain and we calculate. So there is dependency over time for each weight, right? And we need to calculate the contribution of each time step to this weight, right? Now the idea is again change the chain rule, just the chain rule, and nothing too fancy here. But it can get complex when you have long horizon dependency. So for example, for a sequence of 100 characters, the first token could potentially have significant influence on the token and the final position. And this is not really computationally feasible. It takes too long and requires too much memory. And this also, as we will see in a minute, it requires like around 1,000 matrix products before we actually arrive to the very elusive gradient. And this is why gradients usually tend to vanish, right? We have ways to solve this, but it's still a problem, okay? So long contexts are difficult. And we will see that this is the result of high power of matrices, because we have iterative multiplication or product of matrices, and this can lead to divergent or vanishing eigenvalues, which can lead to exploding or vanishing gradients. Now, for efficient computation, this is what is also implemented in PyTorch. Intermediate values are cached during backpropagation through time. This is not new. We save activations in the memory. This is nothing new. Okay. So let's do an example and show you why it can get complex and why do gradients vanish. Okay. Now we're going to consider a simple case. So we're going to talk about 3 time steps. Okay, and we are also going to replace the hyperbolic tangent activation with just identity mapping, so linear activation, right? So instead of hyperbolic tangent, we are going to have just the identity mapping, just for simplicity. Yeah? And we are going to work with hidden states, which is, so we are no biases in this example, okay, also for simplicity, but usually we also have the bias terms. You've seen this above. And so the hidden state at time step t is created as follows. We have the matrix WHX, which multiplies the current input, xt, in the sequence. And we also have WHH, which considers the previous history or hidden state. Okay. The output has its own matrix, so WQH, which is multiplied by HT. Cool. We have the dimensions here, but for now, don't think about it. And the loss function is going to be, we are going to define a loss function for each input in the sequence. So we have element-wise loss function. So for example, cross entropy for each token, and the loss is defined as follows. Okay, and this is the unrolled graph. Okay, and you can see here. So maybe let's move to the board. We have everything on the board, so we can work on the board. Okay, so here is our graph. Here's the loss. Here is how everything is created. Okay, and we start with the forward path, right? So we initialize some h0, so usually like zeros or just random values. And what happens is we have the first input of the sequence, x1. It is multiplied by WHX, and we have WHH that multiplies H0, and this helps us create H1. Okay, so we are here at H1, and then H1 goes to WQH and creates O1, right? And then we move on to the second input of the sequence, so X2. It is again multiplied by WHX, the very same WHX from before, and H1 is multiplied by WHH from before. So you see we need to wait. Okay. So in order to calculate H2, we need to wait for H1 to be calculated. Otherwise, we can't do this, right? And then again, until we reach the third input in the sequence, and we create H3 that will lead to O3. Okay, so this is the forward path. Quite simple, nothing too fancy. Just need to wait a bit. But now we want to talk about the gradient. So we can see we have the edges on the graph. This is the computational graph. And we want to understand how do we optimize WQH, WHX, and WHH. The first thing you see is that there are edges for multiple time steps. So each weight, each matrix, is going to get gradients from all the time steps. Okay, and what we're going to see now is how we calculate them, and it's essentially, so there are many lines here, right? But essentially the rules are the same from tutorial number 3 when we talked about autograd and autodiff, right? Okay, so let's begin from the ending. So let's start from O3. Okay, so we in order to calculate the gradients for these matrices, we need to start from the top. And for the first one, it's quite simple, right? The first line is the first edge is the derivative of the loss with respect to the output, right? So just this one. So we assume that we know what kind of loss function we use. So for example, cross entropy. Okay, so the derivative of cross entropy, and this is what goes to the line here. But now you can see that we need to know the derivatives with respect to ages as well, right? So we want to understand how we calculate the derivative of the loss with respect to age, right? So what we are going to see is that, for example, for WQ okay, then WQ it has multiple lines, multiple edges, and remember the rules. So over the lines we multiply, and between lines we sum. Okay, so for the path that leads from L to WQH from the last time step, then we have the derivative here, which is just the derivative of the loss with respect to the output. And for this edge, so remember what happens here. So WQH is multiplied by age 3. So basically the derivative is just age 3, right? And we multiply, right? So basically WQH, and we do this for all the lines here, right? So it's the same for all the lines here. So basically we have a sum over time steps for the loss with respect to the output multiplied by age t's, right? So just a sum of age multiplied by this derivative here. Okay, so far we've done this part. Now we need to move a bit backwards. So in order to calculate the derivatives here, we need to calculate the derivative with respect to age, right? So for the last time step, it's quite easy, because just like we calculate this edge here, then the edge here is just the WQH, right? Because this is created using WQH multiplied by H3, so the derivative with respect to H3 is just WQH. So far when we reach this point here, then it's just WQH multiplied by the derivative with respect to the output, right? So for the last time step, the derivative of the hidden state is just WQH multiplied by the derivative with respect to the output. What about the previous ages, right? So we need to know the gradients here, right? We need to know what are the contribution of all of the other ages in order to calculate WHX, the gradients of WHX and WHH. Now this can get complex, okay? It's not that simple, and the reason is that now if you'll take a look, the derivative with respect to age, for example, we have two sources, right? We have the source that goes up here, and we have the source that goes right here. So basically we have two paths that we need to consider. So we have the path that goes up, right? So the path that goes up, so it's, we call it, in order to calculate age 3, we needed to consider age 2 multiplied by WHH, right? This is the formula right here. So the derivative on this edge is just WHH, because the derivative with respect to age 2 is just WHH. But it's not enough, because we also have this path here, and this path here is just the derivative like we calculated before. So in this case, the contribution is as follows. So you can see that H2 is multiplied by WQH here, right? So the derivative here is just WQH. Now we have two sources, so we need to sum the contributions. So the first one is WHH multiplied by the loss with respect to HT plus 1, and in this case just the derivative here, right? And for the other path we have WQH. Okay. Oops. Okay, nice. So basically we've got this, and of course it can get quite lengthy computations. So you can actually expand all the recurrent computation and get the following. Okay, so this is where we stopped. And in general, the derivative of L with respect to ht is just a sum over this WH to the power of number of iterations, and WQH and with respect to the loss and the derivative of the loss with respect to the output. Now, when you collect all the terms, you get that WH is taken with the power of the number of time steps. Now here is where we can actually see the problem. So when you have a long context, then this power can grow very large, right? So you have a power of very large power of a matrix. Now the way to look at it is by looking at the eigenvalues. So for this matrix here, if the eigenvalues are smaller than 1, then for a large power, then the values will vanish, and the gradients actually will vanish, right? And for larger than 1, it will diverge, it will explode, okay? So here you can see the problem. Now, the way to solve it usually in the case of RNN is to truncate the time steps, okay, at the computationally convenient size. So basically you define a window size, right? And you just detach the computation from the graph at some point, or you can also do some, for exploding gradients, you can also do gradient clipping. We will talk about gradient clipping later in the course. And basically there are not too many ways to fix that, but other than introducing new more complex mechanisms. So this is what we're going to talk about next, GRUs and LSTMs, and we will see this in a bit. Now we start our computations at age, but we still need to go a bit further back. So WHX and WHH, you can just do as we did earlier, and you can calculate the derivatives, and you will see that the lines, the edges here are just are the derivatives of with respect to ages, what was really complex to calculate, multiplied by x's or ages, depend on what matrix you are calculating the derivative for. Cool. So this was quite complex, and yes, RNNs are complex, but don't worry, you don't need to implement this by yourself. Everything is already implemented for you, but it's important to understand how it works and what happens under the hood, right? And basically it's just backpropagation, but on the unrolled graph, and this is what we call backpropagation through time. Okay, nice. Now we're going to talk about expansions or advances of RNNs, and the main problem is that we want to consider long context, right? We want to be able to model long sequences, and the way we avoid the vanishing or exploding gradients is by introducing more complex mechanisms. So we begin with the most complex one, which is LSTM, and then I'll mention GRU. It's simpler, okay, but maybe the performance will be behind LSTM, and then we'll see an example. So let's begin with the most complex one, which is long-term short memory LSTM. So as I mentioned before, during backpropagation, RNNs suffer from the vanishing gradient problem, which essentially creates a short memory. And LSTM is a type of a recurrent cell that tries to preserve the long-term information. And the idea of LSTM is to introduce gates. So gating, like switches, okay, they are going to control how much information goes in and goes out, okay. And it was introduced in the early 1997, but it flourished, of course, in the age of deep learning, which is the 20s, right? So LSTM introduces a memory cell that has the same shape as the hidden state, engineered to record additional information. So in addition to the hidden state, we are going to introduce another variable, the memory, which is going to be responsible for the long-term memory. Okay, because usually the hidden state is considering only the short-term memory. So we are going to introduce another variable which is called memory. So we're going to have HC and of course our X. Okay, and the way we calculate the values of this memory and this hidden state is now going to be controlled by gates. Now gates are simply sigmoid functions between 0 and 1. So this is why they are like switches. Okay, turn off and turn on. And they're going to control how much information goes in and how much goes out. Okay, and the way we do this is by adding 3 gates to our RNN. So we have the input gate, output gate, and forget gate. Now what you'll see in a minute is that all of these gates are activated by sigmoid, so values between 0 and 1, and this is also helps for numerical stability. But what you'll see is that all of these gates are functions of the current inputs and the hidden states, okay, from the previous steps, of course. Okay, so all of them are functions of the inputs and the past. Okay, and what you'll also notice is that because we initialize them differently, hopefully, or differently enough, they will learn different patterns. Okay, so they will learn to be turned on and turned off depending on their objective. So let's see how it works. Okay? So the input gate, it decides when to read data into the cell, right? So this is so our input gate is here. Okay, so it's taking x and age, right? Calculate some switch, and then it's going to be used to calculate the new memory. We'll talk about it in a minute. The output gate, it outputs the entries from the cell, right? So basically the output of the cell are two terms, are age and c. Okay, so age is going to be used for the current task we are trying to achieve, and c, both of them actually are going to be used in the consecutive time steps. So C hopefully contains the long-term information. And finally, we have the forget gate. And the forget gate is, as you can see, it's multiplied by the memory from the previous step. And basically it tells us how much information we want to take from the past and how much we want to forget. Okay, so just it's a mechanism to reset the content of the cell. Okay. So these are the functions. Okay, so basically all are perform similar computation, but with different matrices, right? So we introduce more complexity. We have more parameters, of course, in an LSTM cell, and now we want to understand what functions are actually implemented here. So we have this C here, this long-term memory, right? And the way we are going to create this C is by first proposing a candidate memory, C tilde, right? And it's going to be calculated as follows. It's a hyperbolic tangent for numerical stability, okay? And it's multiplied by its own set of weights, okay? So this candidate memory is a function of the current input and the past, and basically how much input, how much memory do we want to take from the current input and how much do we take from the past, right? So essentially, hopefully, and this will contain the long-term memory, okay? Now, it's just a candidate, right? So we want to actually create the final memory, which is controlled by the forget gate and the input gate. So the input gate is going to tell us how much information we are inputting into the cell and how much we are forgetting from the past. So both are switches, right? They are values between 0 and 1. So basically they control how much information goes in and how much goes out. Okay? Now, so if the forget gate is approximately 1, right? So basically we actually discard the current input. We don't care what happens in the current time step. We only maintain the past. We preserve the past, right? And of course, the idea here is that it's designed to alleviate the vanishing gradient problem to better capture long-range dependencies. So basically, because the iterative process can lead to vanishing gradients, this memory, this long-term memory, will hopefully won't get gradients from all the steps, because some steps were like were discarded, have not been considered because the input gate was 0. Okay. So the hidden state is controlled by the output gate, and it's multiplied by an activation of the memory. Okay. And HT is what we are going to use for our task. So if you're doing classification, then we are going to use HT from the last entry in the sequence. Okay. Now the idea of gating and bounded output, they both help us alleviate vanishing gradients, and of course they help us with numerical stability when we loop over the entire sequence. So we can see here in animation how it happens in practice. So it's quite complex. So we can see here that all the gates are functions of the current input and the hidden state. We have the forget gate, which controls the memory. We have the output gate and the input gate, which are both help us create the new memory, the new C, right? And then the output gate, which determines age, T, and C. So quite a complex mechanism. Okay, so that's okay if you find it complex. It is. It also has much more parameters. But let's see what happens in practice. Okay, so don't worry, you don't have to implement this yourself. We already have it implemented in PyTorch. So rnn.lstm, and the way we control it is as follows. So we have the input size. This is the embedding dimension, right? So if you decide that each word is represented by a vector of 10, then this is the size of it. The hidden size is just like a hidden layer size. So this is the size of the dimension of agency. Okay, so this is like the hidden layer, right? So you determine its shape, its size, and we also can control how many layers, how many LSTMs we stack. Okay. Now, in this case, there is also an additional parameter, which is batch first. Okay, so you want to tell your network if how is the batch ordered. Okay, so if the batch dimension is the first one, like we always used up to now, then batch first should be equal to. Otherwise, the second dimension is the batch, and the first dimension is the sequence length. And the way it's like this is for historical reasons. Okay. Basically, I think it's easier to work with batch first equals true because this is what we did up to now. But for historical reasons, it's batch first equals false by default. Okay, but we will see that you can change it. So how do we work with this RNN? So we have our input. So our input has 5 words per sentence. Okay, we have 3 sentences. Okay, so in this case the batch size is 3, and the embedding dimension is 10. Okay, so this is the embedding layer. Now we also need to initialize H0 and C0 in the case of LSTM, and their sizes are dependent on the number of layers, right? So we have 2 layers in our case, and we are going to have batch size of 3, and of course the dimension of the agency, in this case it's 20. So how it works, your RNN accepts your input and your initialization of H0 and C0, okay, and it gives you the output, which is the ages from the last time step, from the last layer, sorry, and the last time step, of course, and the Hn and Cn of the last layers. Now, the reason it gives you them back is that because if you want to have another RNN, then instead of initializing, you're going to give it Hn and Cn from the process. Okay, so this is why it gives you them back, but usually what you care about is the output. So if you'll take a look at the shape of the output, so the shape of the output is the same as the input. Okay, so we have the hidden state for each input in the sequence, right? This is why the size is 20, the dimension is 20, and we have 5 tokens, 5 embeddings, and batch size is 3. And similarly, hidden memory, note that they are from the last layer of the LSTM. So they are the last hidden state and memory state for each layer, right? So it's not 5, it's just the last one. It's the 5th output in this case here. Okay, now this is RNN. I'll show you an example of a model in a minute, but I just want to mention that there is also a simpler model, which actually came after LSTM, which is GRU, gated recurrent unit, and it also works on the idea of gating. We have reset and update gates, but they are much simpler, so less parameters and less complexity, but usually they are faster. For when you training, GRUs are faster than LSTM, but at the cost of performance. So usually LSTMs will perform better at the cost of complexity though. So just keep that in mind, and you can see here that it works the very same. Okay, just we don't have the memory anymore, just X and H, but the rest is the same. So let's see an example of for example, a tweet classifier. Okay, and we're going to take tweets from Twitter or X today, and we're going to classify them. So we're not going to actually do it. It's just an outline of what you can do. We have another example of the sentiment analysis, but it's very same for tweets, right? So we want to classify the emotion or the sentiment of the tweet. It's positive, negative, and things like that. So let's see how we initialize it. So of course, nn.module, like always, or module list in this case, but it's very same. we are going to have dropout, of course 1D, and we are going to have an embedding layer. So basically we will have a mapping between the index of a token and the number, and of course the number of the size of the vocabulary and the hidden size dimension, right? We're going to have our LSTMs. So notice here that we use batch first equals true. Okay, and after the LSTM, we actually extract feature from the text. Now we are going to classify it, so we have just two fully connected layers that will map from the output dimension to 1. In this case, we have a binary classification, so just use sigmoid on the output. What happens in the forward pass? So first, we are using LSTM, so we need to initialize agency. In this case, we are initializing them using Savior initialization, and note that they have to be initialized with the same number of layers, the size of the hidden dimension of the hidden size of the the sequence length, and not the sequence, sorry, the batch size, and the hidden dimension, of course. Okay, so we get an x. X is a bunch of indices. We are forwarding it to the embedding layer, so we get now numbers, vectors with the size of hidden dim. Okay, then we are giving it to the LSTM. So batch first equals true. So this means that the first dimension is the batch size, just like here, the number of sentences. And we give it our agency, and we get out the output. We apply dropout on the output. And now we are going to take, so now we're going to take only the final, so you can see here that we are only taking the final token in the sequence. Since we are going to, we need to output just a vector of 1, then of size like 1 on the sequence dimension, then we are taking the final token. And you can also do other stuff, so you can do min, max, and things like that. So as long as you downsample it to be 1 on the sequence size, right? So in this case, we take the final token in the sequence, and we are giving it to the fully connected, and then just doing dropout and sigmoid, and just like regular classification from here, right? Okay, nice. So just the pooling here. So this is the important part. How do we go from tensor that includes the sequence dimension to tensor that does not include the sequence dimension? So here we just use the last token in the sequence, but you can also use other pooling operations. So like min or max or things like that. Okay, now before we finish, I'll mention that while most of today's applications are using attention and transformers, which is the topic of the next tutorial, there are new frontiers in RNNs, so the RWKV, or Receptence Weight Key and Value mechanism, which is also an RNN, but it has many advantages like training in parallel and things like that. So I highly recommend checking it out if you're interested in working with modern RNNs. And it also becomes quite popular, and it also has an alternative for GPT, so chat RWKV. You can go ahead and try it out. It's open source, and of course you can use it in your projects as well. Okay, so in the next tutorial we're going to introduce you to attention and transformers and all the fun stuff that's mostly happening today. So thank you for watching, and I'll see you next time.